All right. So we're going to start off with the second to last section that we're going to look at in this chapter in detail anyway, which is reactions at the benzylic position. And you might remember that way back in chapter 10 in Organic Chemistry 1, we did a whole chapter that dealt with radical chemistry. And you probably remember something called allylic bromination. If you don't, you could go back and take a look at it. That was when we took an allylic compound and we treated it with NBS or N-bromosuccinimide. Anyhow, but first, before we get into that, I want to talk about reactions at the benzylic position. And the first one I want to talk about is oxidation at the benzylic position. And if you're wondering what a benzylic position is, it says here that a carbon directly attached to the benzene ring is called a benzylic position. And so these two carbons that are highlighted in green, those are benzylic positions. If you threw another carbon on here, I don't know, like that, well, then this would be considered the benzylic position, okay? So any carbon that comes directly off the ring is considered the benzylic position. Now, you might recall that if you take an aromatic ring, like a benzene ring, and you try to oxidize it using chromic acid, which is made by sodium dichromate, sulfuric acid, and water, so you mix all those things together, and it makes chromic acid in situ, you get no reaction, nothing happens. Right, and that isn't a big surprise because aromatic rings are so stable. We went over that quite a bit last lecture. The same thing if you take just a plain old alkane, right, without an alcohol in there, you got nothing to oxidize with a chromic acid, and so you would get no reaction from that. Well, what's interesting though is that if you have a hydrogen at the benzylic position, so if you have any alkyl group, and you have a hydrogen on that benzylic carbon, and of course here in this example there's two hydrogens here, but all you need is one. Okay, when you treat that with sodium dichromate, sulfuric acid, and water, it's like the rest of the molecule just disappears. Okay, in fact, the way he describes it in the book is he says the rest of the molecule is excised. Okay, it's removed, or an exorcism is performed on that part of the molecule and it leaves, right? So you end up, you still have the benzylic carbon, it's still there, but it gets converted into a carboxylic acid. And you might think, well, that looks an awful lot like benzoic acid to me, Mr. Dion, and you'd be absolutely right. That is benzoic acid. Now, again, if you don't have a hydrogen on the carbon at the benzylic position, you will get no reaction. And so you've got to have at least one proton here in order for that reaction to occur. Okay, so oxidation at the benzylic position with chromic acid. And you have to be able to remember all of these reagents have to be put together to make chromic acid. So chromic acid is something that's kind of made on site. You make it when you need it, okay? That's why you mix all of these reagents together. You can also do a similar reaction, a similar oxidation at the benzylic position using potassium permanganate in heat. The difference is that this reaction is you're going to end up with a carboxylate ion. Okay, so you end up with a carboxylate, and so you have to protonate that in the second step using hydronium. Sorry, I'm just getting organized here. So overall, what's going on in this reaction is that you're taking this molecule, okay, and in the first step, you're treating it with potassium permanganate, water, and heat. And in the second step, you're treating it with hydronium like that. All right, it says here that benzylic positions are similar to allylic positions and readily undergo free radical bromination. And this is where what I was mentioning at the very beginning of the class, okay? We did a whole section on radical chemistry way back in chapter 10, okay? And that's why I was rambling on about allylic bromination a little bit at the beginning. But similarly, we can take a benzylic position and we can brominate it using NBS, and heat. Now, it doesn't necessarily have to be heat. It could be light. So we'll put here or H nu, which represents light like that. And then we end up making a benzylic bromide. So a benzylic bromide. And you might be thinking, okay, whoop-de-doo, another new reaction in organic chemistry. Wow, you know. Well, what's neat about this is that benzylic bromides are very, very widely used synthetic intermediates. Okay, if you can get to a benzylic bromide, there's a lot of options that come to an organic chemist when she or he does that. Okay, so let's take a look here. It says, and we're just going to run over some reactions. And these are reactions that you know. This is more kind of a chance to jog your memory about some things that you've learned along the way. It says here that a benzylic bromide, tertiary, can readily undergo SN1 substitution. And so what would happen in the first step of this mechanism is that you'd have the loss of the leaving group like that. Now, it doesn't go through the whole mechanism in the book, and I'm not going to go through all the details with you, but you would end up with this carbocation, which of course is resonance stabilized, and then water's going to come in. So that's a solvolysis reaction. Okay, it says here that also an unhindered benzylic bromide. So here we have a primary benzylic bromide. That's going to undergo an SN2 reaction. Okay, and this molecule here, this is called benzyl bromide. And I think I told you this probably in organic chemistry 1 because I know we saw benzyl bromide in that class. Benzyl bromide is a severe lacrimator, horrible lacrimator. If you're like, what does that mean? If you get exposed to it, imagine the feeling that you get when you cut onions and it makes you want to cry. Multiply that by about 100. It's horrible. Anyhow, know it very well. Okay. Anyhow, so that can undergo an SN2 reaction. And if you're thinking again, wow, some more reactions, Mr. Dion. Wow, you're really shocking me. Okay. Well, hold on, hold the phone there. Okay. Look what we've made. We have an alcohol here and an alcohol here. We did a whole chapter on alcohols. So think about all the things that you learned with alcohols. You got a couple of alcohols, right? That's the way you want to think when you're an organic chemist, right? What can I do with this functional group? What else? It says here that we can take a benzylic bromide and we can convert it to the corresponding alkene via an E1 or an E2 elimination. And so here there's only one type of beta proton in this molecule, and the ethoxide is going to pull off one of those protons. I'm just drawing one for instructional purposes only, right? We get the elimination reaction like that. And part of the driving force for this reaction is that now you have a fully conjugated system. You see the double bond is conjugated to the aromatic ring, and that renders it quite stable. So having a fully conjugated system like that. This is another reaction that students seem to forget once in a while, but it's an important one. It's an E1 reaction. We don't look at a lot of E1 reactions in this class, but remember what happens here is when you take an alcohol and you treat it with concentrated sulfuric acid, you drive water out of it. Okay, you remove water and you end up producing an alkene. All right, and you should be able to recognize the mechanism of an E1 reaction, right? You are first going to convert the hydroxyl to a good leaving group, and it's going to leave, and you do a proton transfer to produce the alkene. So again, I'm just going to go backwards in my slides here. I don't do that a ton in this class, but all of these reactions, these two here and these two here, these are all things that you already knew before coming to class or should have known. But, you know, the reason that we show you these in this chapter is because, you know, you think, okay, well, if I was to have, let's just go over this. If I was to have, you know, a compound with a benzylic hydrogen and I oxidize that, right? Either using chromic acid or permanganate followed by an acidic workup. Either way, I could end up with a carboxylic acid. Well, surprise, surprise. We're going to do a whole chapter where we talk all about carboxylic acids and their derivatives. It's chapter 20, so something to look forward to. And I'll just tell you right now, there's a lot of things you can do with a carboxylic acid. But anyhow, I digress. You can brominate either one of those. You can make an unhindered benzyl bromide like this. You could make a hindered bromide like this. So you can do elimination reactions, substitution reactions. Look at this. You can make alcohols. You can make an alkene. Look at this. Chapter 8, talk about alkenes. Remember, way back in Organic Chemistry 1, I do this every time I teach Organic Chemistry 1. I always make a point of kind of pausing at the beginning of Chapter 8 and saying to my students, you know, this is where the reactions really start. Think of all the things that you learn in chapter 8. You know, Markovnikov addition, anti-Markovnikov addition, epoxide formation, dihydroxyl formation, right? You learn all these different reactions. It's, you know, give me an alkene, and there's a lot of things that you can do with an alkene. Anyhow, this is, and if you're thinking, wow, you know, this is really opening up a lot of opportunities for me as a budding organic chemist, and it's absolutely true. Absolutely. Well, with that in mind, let's take a look at some practice problems to see if we fully comprehend just what went on here. And it's not meant to be, you know, a mind-boggling problem here. It just says draw the expected product when each of the following compounds is oxidized with chromic acid. So let's practice drawing out the reagents that are required to make chromic acid. And in order to do that, you need sodium dichromate, a red solid. Go get some sulfuric acid, and that always comes in a bottle with a yellow cap. It's just, you know, I don't know, commonplace. Anyhow, and you add water to that. You mix that all up, and you get chromic acid. Could anybody? I'm going to throw this out to my students. Can anybody just name the compound? Just tell me what the name is of the compound you would get from this reaction. Oh, here it is. Yeah, Andrew's got it. It's benzoic acid. Yes, you would just end up, right? You would just end up forming benzoic acid, and so you don't lose any carbons here. You just make benzoic acid. And why can you do that? Because we have 1, 2, 3 protons here at the benzylic position, so no problem. The same thing applies to the next question. We have two alkyl groups. We have hydrogens on both of them, benzylic hydrogens. We have 1, 2, 3 here. We have 1, 2 over here like this. We're going to treat it with the exact same reaction conditions. Bromic acid. Can anybody tell me how many carboxylic acid functionalities would be in this? How many carboxylic acid functional groups would be in here? Yeah, Adriana says 2, Luke says 2, Sarah says 2. I'll go with the 2s. Yeah, the 2s have it, right? We're gonna have something that looks like this. We're gonna have 1 carboxylic acid here, and we'll have another carboxylic acid here. I don't ask you to know the name of this compound, but this is called isophthalic acid or metaphthalic acid, I think. Either one's fine. Anyhow, again, you don't have to memorize that. All right, there we go. And I'm going to give you a second to draw the product of the next one. Okay, can anybody tell me how many carboxylic acids will there be in the final product here? Yes, exactly. Thanks, Sarah. Yeah, it's good. Thank you, Kate. Good. There's going to be 2. Again, there's only going to be 2 because there are no, and let's write it in a different color. No benzylic hydrogens here. And so we're not going to get any oxidation at that tertiary carbon. However, we will get oxidation at the other ones, right? Because we have 2 hydrogens here. And on this sec butyl group, there's a hydrogen right there. And so we can draw our final product. We're going to have our aromatic ring like this. Okay. We're going to have 1 carboxyl group over here. We're going to have another carboxyl group meta to it like that. And then we have our tert butyl group right here. Just like that. Kind of cool, huh? Some neat reactions there. All right. That covers all of section 17.6. Like, that was quick. Yeah, that's the whole thing. That's all of section 17.6. And yeah, there we have it. Let's take a look at section 17.7, the reduction of benzene. And this is the last section that we'll cover in detail. It says here that under forceful conditions, You can hydrogenate benzene to cyclohexane. However, I wouldn't want to be the guy that has to do this. I've never done any reaction at 100 atmospheres of pressure. That's pretty high pressure, right? So we'll say here, really high, very high pressure. I've done reactions at maybe 30 atmospheres or 50 atmospheres at the most, okay? And then we also have high temperature, okay? So it can be done, all right? It can be done, but more commonplace, if you remember back in Organic Chemistry 1, I think I showed you a picture of a fume hood where somebody was doing a hydrogenation. And hydrogenations, you usually do it, with just a round bottom flask. And if you can get away with it, you put a rubber stopper on the top of it. And what you would use is just a balloon, like a party balloon. Okay, so you would literally just put a needle in it, and then you have like a balloon from the dollar store, and you have hydrogen in it, and that will put a positive pressure of hydrogen on your reaction mixture and will hydrogenate it. So, something like 2 atmospheres, that's not a very high pressure. That might be like a thick-walled balloon or something like that. So you probably remember this guy right here. This is styrene. If you take styrene and you hydrogenate it, okay, so treat it with hydrogen, but 25 degrees Celsius, that's room temperature pretty much, okay? And at 2 atmospheres, again, that's only double atmospheric pressure. It's not very high pressure. You can just selectively hydrogenate that exocyclic double bond. I shouldn't say exocyclic, the vinyl group, okay? So you can selectively hydrogenate this alkene and keep the aromatic ring intact, all right? Anyhow, so that's a pretty useful reaction. And that would be something that would be useful to an organic chemist. But there's another reduction that we can do, and that's called the Birch reduction. It's a really old reaction. It's named after a chemist named Arthur Birch, okay, who invented this. And it says here that benzene can be reduced via Birch reduction by taking benzene and treating it with sodium. So that's literally sodium metal. The sodium metal, which is a group 1A metal. It's a soft metal. Methanol, so this is methanol, okay, methyl alcohol, and ammonia. You mix all those things up, ammonia, okay? And it says here that the mechanism is similar to the dissolving metal reduction of an alkyne that we looked at in chapter 9. So if you remember the radical anion, remember when we took something like, I'll just give you one example off the top of my head. If we took 2-butyne and we treated that with sodium and liquid ammonia, remember what happened? We ended up forming the radical anion. Anyhow, look something like this, and then you had the negative charge here, right? And we said that they want to get away from each other as far as possible, and that's why you end up with a trans. Alkene like that. Anyhow, so sodium metal reduction, okay, the Birch reduction. And what you do is you end up basically eliminating one of the pi bonds. You lose one pi bond, and you end up with 2 sp3 hybridized carbons in the molecule like that. And this molecule would be called 1,4 cyclohexadiene. So you would end up with a 1,4 cyclohexadiene. Let's take a look at the mechanism. And I think you should know this mechanism, right? Sodium, again, is a group 1A metal, so it has 1 valence electron, right? If you think about the valence electrons for any group 1A metal, they always end up in NS1, right? So you always have just 1 valence electron. Well, that single electron, okay, is transferred from the sodium to the aromatic ring, and we end up with a radical anion. Why is this called a radical anion? Well, what's it got? It's got a radical right here, and it also has an anion up here. So after the electron transfer, then you do a proton transfer from the methanol. You end up with a radical. What's going to happen is sodium is going to donate another electron, okay? So the sodium donates another electron to make an anion. It's not a radical anion this time. It's just a plain old anion. And then we do another proton transfer like that. And there we go. We end up with our 1,4 cyclohexadiene. And so the way that David Klein helps his students to remember this is that he says the way you can remember this mechanism is that it goes electron, proton. Electron, proton. So just 1, 2, 3, 4, electron, proton, like that. It's probably one of the easier ways to memorize this mechanism. All right, it says note that the birch reduction does not completely reduce the ring. The product has sp3 hybridized carbons on opposite ends of the ring. Told you that a few minutes ago. But here's, in memorizing reagents, you guys are all experts at memorizing and rationalizing mechanisms by now. But this is kind of the key to 17.7. This is the kind of thing that we're going to ask you about, is knowing where the reduction is going to occur when you have substituents on your aromatic ring. So let me show you here. If you have an electron donating group, okay, it says here the presence of an electron donating alkyl side group provides regioselectivity. So why is an alkyl side group electron donating? That's based on, who can tell me what concept that's based on? Why is an alkyl group electron donating? I'll give you a clue. Something that we learned in Organic Chemistry 1. Starts with the letter H, ends with hyperconjugation. That's right, hyperconjugation. Okay, hyperconjugation. Every organic chemistry student should know what hyperconjugation is, and that alkyl groups are electron donating. And so what's going to happen is, if you take an aromatic ring that has an alkyl group on it, remember that's an electron donating group. Now, electron donating, we put EDG for electron donating group. So this is an EDG, okay? The carbon that has that electron donating group attached to it is not going to be reduced. Let me show you why, okay? It says here that an electron donating group destabilizes the radical cation, and so the reduction does not occur at the carbon possessing the electron donating group. Okay, well, what does that mean? It says here that if you formed the radical, I shouldn't say radical cation, I should say radical anion. Oops, I'm going to change that. Jesus. A radical anion. Okay, fix that. Okay, you would end up with an intermediate that looks like this. I'll draw it out for you. You'd have your aromatic ring, okay, like that. You have your electron donating group, okay. And if you were to reduce to make this compound, which you're not going to get, you'd have this as an intermediate where you have an anion here, okay, like that, okay. So now you've got an electron donating group donating electrons towards a negative charge, okay. So I'll put here, we'll just write by this, disfavored, okay. It's going to be highly unstable. All right, there we go. So what about if we have an electron withdrawing group? So an electron withdrawing group, we'll use EWG to represent that. Well, why is this? It says here acetophenone. It says that this is an electron withdrawing group. And it is. This is an EWG, but why would that be? Well, you should know why, and it's because there's a dipole going from the carbon to the oxygen like this. You could even draw a resonance structure, right, that shows a negative charge on the oxygen, positive charge on the carbon, and you could delocalize that around the aromatic ring, so you should be able to rationalize that. But what's going to happen here is that you are going to get reduction occurring on the carbon where the electron withdrawing group is located. And the reason why is because if we draw that intermediate, it would look something like this. Oops. It would look something like this. Okay. And then if we had our radical anion like that, well, of course, that's going to be stabilized, right? Because we're going to have an electron withdrawing group next to a negative charge, and that's going to stabilize it, okay? And so all you really have to know is what's an electron withdrawing group and what's an electron donating group. And if you have an electron withdrawing group, you are going to reduce at that carbon. If you have an electron donating group, you are not going to reduce at that carbon. I'll give you a heads up. I'm not going to ask you to draw the mechanism. You just have to be able to predict the products. And so with that in mind, let's move ahead and let's take a look at some reactions here. It says propose an efficient synthesis for each of the following transformations. So we'll start with C. Start with C. Well, what are my possibilities here if I have C? I have toluene. There's not much that I know that I can do with that besides a combustion reaction, or hyperconjugation would have probably been in chapter 1 or chapter 2, first couple chapters. Yeah, so what can I do here? Can anybody give me an idea where I would start in C? What might be a good approach to starting C? I'll take anything. There's not much, but there's a reaction that we learned today. A reaction that we went over at the beginning of this lecture. Yeah, somebody says radical bromination. Couldn't agree more. Somebody says NBS and heat. Yep, that's right too. So it's just radical bromination. You both are meaning the exact same thing, I know. So let me just draw. There's not a lot of room here. But if we were to treat this with NBS and we were to heat it up, okay, we would end up with this guy. We'd end up with this molecule, benzyl bromide. Okay, so now what are we adding? You guys recognize this right here? This is a nitrile. And where does a nitrile come from? In order to make a nitrile, okay, you'd want to have a cyanide. Okay, and cyanide, this is cyanide, is a good nucleophile. So if you were to treat benzyl bromide with sodium cyanide, that's going to be a good nucleophile for what? For an SN2 reaction. So that's going to knock the bromine out like this, and you end up with this compound, which is benzonitrile. No, sorry, that's not benzonitrile. That's oh shoot, I can't think of the name. Escapes me right now. Anyhow, there you go. Give me a thumbs up if you follow me on that. So first, benzylic bromination followed by an SN2. Nothing more than that. Just benzylic bromination and an SN2. Anybody follow me on that one? Okay, good. All right. All right, good. Thanks, Sean. Thanks, Kylie. Good. Okay, let's try another one here. The next one. Do we have a benzylic hydrogen in this next compound? So this would be cyclohexylbenzene. Yes, we do. We do have a benzylic hydrogen right here. So we can take the same kind of approach. All right, we can treat this molecule in the first step with NBS and heat, right? And then we would end up with a bromine at this position. Okay, now that is a hindered bromine, right? That is tertiary. That's a tertiary alkyl halide. So if I want to put a methoxy group in there, can anybody tell me? I'll just tell you, there's only one more step to this reaction sequence. Can anybody tell me what I would do? And it's something that we looked at this morning. What would I do? What would I do with that tertiary bromide to get it to make that methoxy group? No, I don't want to treat it with a base because it's hindered, right? If I take a hindered alkyl halide and treat it with a base, then I'm going to do an elimination. If you were to treat this with sodium methoxide, you would end up ripping off this proton and you'd end up with an alkene in here. Okay, so that's not going to be an option. Let's what does somebody say? Somebody else says methanol. Let's back up in our slides here. We got time. I'm going to back it up. Where was it? Right here. Okay, if we take a tertiary benzylic bromide and we treat it with a polar product solvent, we can do an SN1. So instead of water being our solvent, right, if we have, go back on the question now. If we have methanol as our solvent, right, what's going to happen is that, I'm running out of space here, aren't I? That this leaving group is going to leave, and you're going to end up with, you'd end up with this compound, this resonance stabilized carbocation, and then methanol can come in, right? back, and then by a proton transfer, you'd end up with a methoxy group like that. Okay, and so the second step would be to treat it with methanol like this. All right, I'm going to find a blank document, so I'm going to stop projecting my screen here just for a second. And just so I have more space to write, just give me a second here. While I'm doing that, you guys try to answer the next one. Okay, can you all see my blank screen now? Somebody says, why adding water and then following with sodium methoxide wouldn't work? Because if you added water, you'd end up with an alcohol, and then sodium methoxide would just deprotonate the alcohol, right? If you were to take this compound and you were to treat this with NBS in heat, you'd end up with this tertiary alkyl bromide, or benzyl bromide, I should say, like that. Then this group is going to leave, okay? You're going to end up with this carbocation. And if you were to add water to that, right, if you put this in water as your solvent, okay, the water is just going to, oops, I left my carbocation there, didn't I? You're just going to end up with this, okay, this intermediate. So let me redraw my arrow going like this, right? And then after the proton transfer, so I'll skip that step, I'll just put another arrow here like this, you'd end up with this tertiary alcohol. And then if you took that and treated it with sodium methoxide, all you would end up with is this alkoxide like that. That's what you'd have, okay? All right, so that is why, so let me erase all that spinach. Delete. That is why when we treat this with methanol, CH3OH, this goes all the way back to chapter 7. If you're wondering, where are you digging up these reactions? This is all in chapter 7. Okay, this is a solvolysis reaction. You end up with this guy, like this, which looks like this, and then another molecule of methanol will be protonated, so you end up losing H plus, and you end up with the final product, which is this. There you go, like that. All right, does anybody come up with an answer for E, or have any idea where to start, where to end? Let me write it down here. So what is it? 17.18 E. All right, so we start with this molecule. Looks like it's isopropyl benzene. It's got a common name. It's fumine. You don't have to have that memorized. But there we go. Yeah, I suppose you could have done a Williamson ether synthesis at the end. It's just a lot longer route to do it, okay? So yes, if you were to throw in iodomethane at the end, yeah, sure, that would work. It's just very long. It's a few more steps, okay? Anyhow, who's got an idea about where we could start here? I'll give you a clue. It's a reaction that we looked at this morning. It's really our only option. Here would be to take cumene and do what with it? We really only have one option here, people. Well, we got two. Combustion is one. Does anybody have an idea what the other option would be? It's not. So yeah, if I oxidize it, I'd end up with a carboxylic acid. So look, if I was to treat this with chromic acid, Cr2O7, H2SO4, and water, I'd end up with benzoic acid. But the problem with that is that I haven't learned any reactions yet about what I can do with a carboxylic acid. So I'm going to put that one, I'm going to scratch that one, okay, because we're not sure what to do with that yet. So we'll put that there. It might be an option in the future, but today it's not an option. So our first option is going to be, or our only option is to treat it with NBS and heat. Then we're going to have this compound right here. There we go. Okay. Now, in terms of the ketone, okay, if I think of the final product, which is acetophenone, I'm sure, you know, some of you might be like, I don't remember this reaction that well, but think about it retrosynthetically. Couldn't we make this compound from, I mean, we don't have that many ways to make a ketone, but couldn't we make it from this alkene, right? Couldn't we do an ozonolysis reaction, right? And break that off like that? I'd say that's probably our best option. And so if we were to take this tertiary alkyl halide, and if we were to treat that with sodium methoxide, we're only going to get E2. And so we're going to pull off one of these protons. So we have our methoxide like this, pull off the proton, do an elimination reaction, and then we'll end up with this molecule. We'll end up with this guy. And then all we have to do is the ozonolysis process. And what's the ozonolysis process? The first step is to treat the molecule with ozone, and the second step is to treat it with dimethyl sulfide, like that. And that's going to give us our desired product, which is acetophenone, like that. What do you think? Who nailed it, or who knew what to do as soon as they saw this reaction? Right, as soon as you saw that, you're like, I know what to do, right? Just make an alkene and move on with life. Because that's usually the way students feel about these kinds of problems, is that they'll say, okay, well, the last step, I just kind of had to jog my memory on ozonolysis. Okay, anybody there? Can you hear me? Okay. All right, good. Sorry, I thought I was alone there for a second. You guys want to try some other problems from this question? Why don't we just try a few? Okay. We're all tired. I hear you, you guys. I'm beat. All right. Who's in survival mode this week of class? You know, some people wish for world peace, millions of dollars. I would just like a day with no email. That's what I would like. A day without email. I told my wife the other day, you know, I would just like 10 minutes to sit outside in a chair, and I don't even have that. All right, so anyhow, let's give this one the old college try. So we want to go from this isopropyl benzene, and we want to make this compound. I think this would be good practice for everybody who's hearing the sound of my voice. Does anybody have an idea what we do here in the first step? Give you a clue. We haven't got many options. Burning it is one of them. And what's the only other option that we have? Yes, thanks, Kate. I appreciate that. Yeah, you're absolutely right. 100% is that you're going to treat that with N-bromosuccinimide, and you're going to heat that up, and you're going to end up with this compound. Okay, you end up with this tertiary benzylic bromide, like that. And then the next step, and I want you to make sure that you review this. This is the solvolysis reaction. This is an SN1 reaction, okay? And if we're putting a hydroxyl group on here, And if we just need to put a hydroxyl, we're just going to take the molecule and we're going to put it in water. And there you go. That's the end. So if you need to review these, so review, I'll put a review with a question mark if you need to review. And again, this is called solvolysis. Okay, there we go. Let's take a look at another one. So this is 7.18. What's this one? B. Maybe I should have started with the easier ones if you're that tired. Anyhow, up above, we're taking what if we wanted to take ethyl benzene? Okay, there's ethyl benzene, and we just want to make styrene. Maybe these questions are a little easier. Just want to take ethyl benzene and make styrene. Who's got an idea for a first step? And Eric is going to provide the second step. Does anybody have an idea for the first step? Not a trick question. It's not bromine, but NBS. Yes, you want to brominate, right? Because you've got two benzylic hydrogens here. And so you want to brominate. And to do that, you're going to use NBS. Let's try light this time. Let's be spicy about it. Okay, let's try something new. Okay, and Eric, what's going to be the reactant that I need to take this compound, secondary alkyl halide, and make styrene? Or anybody. I'm just picking on students that I can't even see. It's not fair. Eric says T-butoxide. Well, you know what, Eric? I think that T-butoxide is probably the best choice in this case. I would accept either of these, okay? In this case, and the reason why is because Eric and I had this conversation in the lab yesterday at UCCS. He said, sometimes we use this, and then sometimes we just use this, and sometimes it gets confusing. Well, if you go back to figure 7.20, so this is way back in chapter 7. It says, okay, when you have a strong base or a strong nucleophile, so strong base, strong nucleophile, okay? And if your substrate is primary, second, got it properly, is it? If your substrate is primary, secondary, or tertiary, what's going to happen, okay? So then it kind of breaks it up into this. I think you probably all remember this table. But it says that if you have a primary alkyl halide, you're going to get some E2, right? You're going to get some E2, but it's mostly going to be SN2, okay? If you have a secondary alkyl halide, like I have here, okay, it says you're going to get mostly E2, and you're going to get some SN2. And then for a tertiary alkyl halide, it said you're only going to get E2. So it doesn't matter what you use, okay? Now, there is a caveat to this, okay? And that is with the first two, okay? With these first two here, okay? If you use T-butoxide as your strong base, because when we have strong base, strong nucleophile, we say it's hydroxide, methoxide, and ethoxide, okay? But it's a little bit different for T-butoxide. He's a little bit different player, okay? And if you use T-butoxide, in the first case, you're going to mostly get E2. Okay? You're mostly going to get E2 with T-butoxide. And in the second one, you're only going to get E2. So in the second one, only E2. Okay, and if you're wondering, like, you didn't go over that, well, it's not in the table, but I did go over it because it is covered in the book in Organic Chemistry 1. So that's kind of a little nuance. So that means that Sarah and David and Eric are all right. I would accept all of those. I would accept, in this case, I would accept either one of these. You could use sodium ethoxide, sodium methoxide. You could use potassium T-butoxide. Now, T-butoxide, according to what I just told you, since this is secondary, is going to be higher yielding, right? You're only going to get E2, okay? But again, if you were to take the secondary and treat it with ethoxide or methoxide, you're still going to get mostly E2, all right? No matter what. T-butoxide is a better choice, but I'll tell you right now, The book doesn't split those kind of hairs. Okay, it's not like, oh, you get this wrong if you know. There are cases when you do have to choose only t-butoxide. Yes, if you want to make a Hoffman alkene, sure, but here regioselectivity isn't even a consideration. There's only one type of beta proton to pull off. There's only one possible alkene form. Does that help a little bit? Yeah or no? Some good teaching. All right, good. Anyhow, I hope that clears it up a little bit for you. Again, if you go back into chapter 7, it does go over that. He mentions how t-butoxide is a bit of an anomaly. So we could put either one here. So why don't we put, for now, we'll put either one of these. And I don't even know what it says in the book. My guess is that in our book, he probably says sodium methoxide because he's hooked on it. Let's use that for everything, but whatever. Put it right here. There. We'll say, and we'll say, I think Mr. Dion thinks that the book, I tell you, this guy's addicted to sodium methoxide. So there we go. Anyhow, try another one. The next one, F. Try F. After this, we'll look at some practice problems that I posted to Canvas. Did you guys notice that I posted some? I think it was last night I posted some. And if you didn't notice, they're up there. In the chapter 17 module, I put a few practice problems. I'll put the solutions in the near future. Okay, so this one here. Ooh, this is a good one. I like problems like this. We're going to take this molecule and we're going to make this big old alcohol. Okay. Look, I know you might be tired, but you're going to have to wake up because synthesis is only going to get more complex, right? Think about all the things you've learned, you know, green yards, epoxides, all that stuff. You're going to have to know that. You're going to have to be, as I say, Johnny on the spot, like those kind of reactions, okay? So I'm going to walk through this one instead of me just asking you and asking you and asking you. But how would we make this compound? This is a good one retrosynthetically. But when I see this compound, I think if I could have this compound where I had this epoxide, if I could make this epoxide, I could treat it with ethyl magnesium bromide, so ethyl Grignard, right? And that ethyl group is going to act as a nucleophile and it's going to crack this open, right? Like that. And I bet you that you could all figure out how to get from ethyl benzene to, 2-phenyloxyrane, right? I bet you can all figure out how to do that, okay? And I'm going to walk you through it right now. The first step is going to be the bromination reaction, right? Because we have 2 benzylic hydrogens here. And then that means that we can treat this with NBS. We make a benzylic radical, which is stabilized and it reacts with bromine. Okay, and we end up with this compound. So we end up with this guy, like that. Remember that's secondary, so you could treat it with t-butoxide. You get exclusively E2. You could treat it with sodium methoxide. That will work too. Let's just write sodium methoxide. And then you're going to end up with what molecule? Styrene. Okay, everybody loves styrene. Okay, there you go. You have styrene. Now, how would I make an epoxide from that? I would treat it with MCPBA. Okay, or peroxyacetic acid. Either one will work. And we would end up with this compound. End up with this 2-phenyloxyrene. Okay, and then to make the final product, in the first step, we're going to treat it with ethyl magnesium bromide. So ethyl magnesium bromide. Put my lone pair here. That's going to do an SN2. It's, remember, a strong nucleophile is going to attack the least hindered carbon on our oxyrane. So we crack that open. We're going to end up with this intermediate. Sha. 1, 2, 3. Yeah, good. We're going to end up with this intermediate. And then in the last step, we just put water on it like that. And if you were to write H2O, Dr. Anderson told me that he's previewing the 4th edition of this textbook. And he said that in the 4th edition, instead of putting water, they use H3O+, which is more correct because you treat it with an acid, then you end up with water, which is neutral, instead of ending up with hydroxide, which just seems kind of ridiculous to me. Anyhow, that's one option. There is another option for solving this problem. There is one more option. I'll show it to you quickly. Okay. I'll just write the whole thing in blue. So if you were to take this compound, okay, and we were to start the same way, we were to treat this with NBS in light, we'd end up with the benzylic bromide, like that. Then we'll treat that with sodium methoxide, and we end up with styrene. Doesn't look too different yet, does it? Okay, so we end up with styrene. I'm going to draw my styrene like this. Then what if we did an ozonolysis reaction of this? What if we treated it with ozone followed by dimethyl sulfide? Well, what are we going to have then? Then we're going to have this aldehyde. This is called benzaldehyde. You'd have this, okay, right, because you have a hydrogen here. Well, now you can take this and you can treat it with a Grignard, but now you're going to need a Grignard with one more carbon. You need propyl magnesium bromide. So propyl magnesium bromide, which would be magnesium bromide positive, 1, 2, 3. Oops, that's 4 carbons, Mr. Dion. There we go. And then that's going to do an SN2 like this. Okay, so then you'd end up with what? You'd have that same old alkoxide. Sorry, yeah, the same alkoxide that you had before, like that. 1, 2, 3, and then you'd put water on it, that, and you'd end up with the product. And so either of those are going to work perfectly well. Let's see, this one is a total of what? 1, 2, 3, 4, 5, 6 steps. What's the other one? Got a total of 1, 2, 3, 4, 5. Yeah, that's close enough. I'd give full points to both of those. Both equally elegant, we'll say. All right. Well, with that, if you go to the Chapter 17 module on Canvas, I've published a bunch of practice problems here. There's some nomenclature, there's some reactions. It's a real smorgasbord of just happiness. And it's stuff that you can really enjoy. Some good organic chemistry problems. Is anybody like me? When they get tired or stressed, they can just sit down with some good OChem problems and maybe look at a mechanism, fall asleep in a chair. All right, you're probably like, I got you on the organic chemistry and fall asleep in a chair, but not the rest of it. Okay, I'm going to give you 3 minutes to look at as many problems as you can. Start at the first one. See where you can get. I'm never going to ask you to name a polyaromatic hydrocarbon, but just in case you read that section in the book, I'll give you 3 minutes. All right, let's give it the old college try. The first few aren't that bad, I don't think. What's the IUPAC name of the compound in number 1? Get an idea. Sabrina, are you there? You have an idea? Or anyone? Excuse me. All right, somebody says B. I like the way you guys think. Yes, all my students are saying B. Yeah, because, and if you're not following us, well, you can see that here we have a phenol, right? And then we assume that the carbon that has the hydroxyl is carbon 1. So we have 1, 2, 3. So this would be 3-bromophenol. Good. Let's move on to the next one. Anybody have an idea about this one? We'll go through these first ones kind of quickly. Could you also say meta for the first one? Absolutely, you could, but it's not an option. But yes, you also could say meta for that one. It says here, what's the IUPAC name of this compound? Sarah says that it's D. I tend to agree with you, Sarah, because we have what? We have an aniline here, right? This is aniline, like that. And then if we count our carbons, 1, 2, 3, 4, we have a 3-bromo and a 4-nitro aniline. There we go. Okay, let's move on to the next one. Sometimes my students will struggle with alkyl groups at this point in the year. They start to forget them a little bit. Does anybody have an idea for this one? Adriana says D. Yeah. Okay, somebody else. Yeah, Luke says D as well. Sure. Here we have a phenol again. You guys remember this group right here, this alkyl group? This is a sec-butyl group. Okay, you got to know the sec-butyl group. You guys remember this one? If you have this would be an isobutyl. Sometimes students forget isobutyl and sec-butyl. So this is 4. If we number here, 1, 2, 3, 4. This is 4 sec-butyl phenol, which is D. Good. All right, we're cooking on these. All right. Does anybody remember what the common name of this compound was? I went over it with you on a slide. For number 4, what would be the common name? It's metazylene. Yes, exactly. So remember, whenever you have 2 methyl groups on a benzene ring, it's a xylene. So this would be metazylene. Okay, if you had 2 methyl groups like this, that's paraxylene. And then if you have 2 methyl groups ortho, of course, you probably see where I'm going. That's orthoxylene, like that. Okay. Hey, this one's a little trickier. Right now we're getting into something that's a little bit trickier. We have an IUPAC name for the following compound. Does anybody have an idea on this one? Some might take a second. Or does anybody recognize a parent in this one? Is there a parent compound in here? Not in a parent compound, a parent compound. There's a common, yes, thank you, Eric. Absolutely, right here. Yes, there we go. There's a benzaldehyde. Benzaldehyde, good. Okay, so if we have benzaldehyde, remember, we always want to seek to give the first substituent the lowest possible number, and there's a substituent right next door, and so we start numbering 1, 2 ethyl, 3, 4 fluoro, 5 methyl. So those are all the groups that we have, and they actually come in alphabetical order, right? E comes before F, and F comes before M. And so when we put all this together, we get 2 ethyl, 4 fluoro, okay, fluoro, 5 methyl benzaldehyde. Now that I look at the structure, I can see that my students might think, well, Mr. Dion, why didn't you name this as a toluene derivative, right? Why didn't you name that as a toluene derivative? Well, the reason why is because of the order of precedence of functional groups. And this has come up a few times in our class. There's no table of order of precedence of functional groups in our textbook, but I have told you a few times that whenever you have a functional group that's got more oxidation, like a higher oxidation number of the carbon, that's always going to have a higher order of precedence. And so the benzaldehyde would be the parent over a toluene. All right. The next one, I didn't really cover the part about polyaromatic hydrocarbons. Please take a look at it. But this molecule is called phenanthrene. Phenanthrene, carcinogen. The next one is a nomenclature problem where we have a structure to draw. So it says 3-isobutyl, 5-isopropyl aniline. So why don't we start by drawing aniline? Start with that. So we have our aniline, looks like this. It's an amino group like that. And then if we number the carbons, 1, 2, 3, 4, 5, 6, like this. On the third carbon, we'll put an isobutyl. So that looks like this. We have 1, 2, 3, 4 carbons like this. And then on the fifth one, we put an isopropyl, which looks like this. And there you have it, folks. There's your product. Okay, or there's your product. There's your compound. 3-isobutyl, 5-isopropyl aniline. I'm going to ask my students if they can answer this question because I did talk about MO theory quite a bit in Organic Chemistry 1 in Chapter 2. We spent quite a bit of time talking about MO theory. It says here that when you have molecular orbitals that are equal energy, what do we call those? When you have two MOs, remember we looked at the Frost circles? Okay, we'll just do the Frost circle for cyclobutane, for example. Okay, so we made the Frost circle, and then we drew the square. Oh, good gravy. Anyhow, and then we said, okay, well, you have molecular orbitals. Oops, what did I do? Is that all gone? I bet you it is. Just my luck. Go. It's Friday. Okay, so if we try that again, put something like this. And then we put the molecular orbitals. We have one here, one here, one here, one here, right? So this is a bonding MO. This is an anti-bonding MO. These ones here are non-bonding MOs. But when I have two MOs that are the same energy level, you guys remember what they're called? I'll give you a clue, or I'll try to help you, I guess. Think about general chemistry, right? If you have three p orbitals, you have, px, py, and pz. What are these orbitals? Since they're all the same energy, do you guys know the word that we use to describe them? You might use the same word to describe a career criminal. Anyone? No? Okay, they're called degenerate. Degenerate orbitals. When you have orbitals that are the same energy level, those are called degenerate orbitals, whether they're atomic orbitals or molecular orbitals. Okay, let's move on from there. Question number 9. According to MO theory, how many molecular orbitals are formed when 6 p orbitals of benzene overlap? We have the benzene molecule, right? We looked at this and we said, okay, well, there's all these p orbitals and they all overlap and we get different molecular orbitals. Does anybody remember how many molecular orbitals you get from these 6 p orbitals? Yeah, thanks, Sarah. The answer is 6. Yeah. Remember that the number of atomic orbitals is equal to the number of molecular orbitals. Okay, they're exactly equal. Alrighty, let's move on from there. For a compound to be aromatic, it must have a planar cyclic conjugated pi system along with a blank number of electron pairs. So if you think of benzene, okay, it's got 3 electron pairs. Anybody can answer that for me? Yeah, it's an odd number of electron pairs. Perfect. Yes. Good. Okay, an odd number of electron pairs. All right, let's get into some aromaticity questions. What time is it? 9:10. Do a few of them here. It says, which one of the following compounds is aromatic? Well, if we look at the first compound, that's a cyclopentadiene cation. That's anti-aromatic, right? Because this carbocation, right, the carbon with the carbocation on it is sp2 hybridized. So that means there's a p orbital here, right? And you have p orbitals here, and you have a total of 4 pi electrons. So that's a non-Huckel number. That's 4n, where n is equal to 1. And so that is actually an anti-aromatic compound. It's one of the few anti-aromatic compounds that we looked at. The next one, I'm going to kind of go over it quickly because we looked at it in detail. It's cyclobutadiene. It is also an anti-aromatic compound, like that. Okay. The next one is not aromatic whatsoever because it has an sp3 hybridized carbon just sitting right there. And so that definitely doesn't have a p orbital on it. And so we don't even have to consider the lone pairs there. And the last one is thiophene. We looked at this one on Wednesday. And we went over the rule that states on a heteroatom, like this sulfur, that one of the lone pairs can go into a p orbital if it will make the compound aromatic. And there's a p orbital here, there's one here, there's one here, and there's one here. If one of those lone pairs goes into a p orbital, and then we have a Huckel number of electrons, right? We have 4n plus 2 when n is equal to 1, then we have 6 pi electrons. And so we would have a continuously overlapping system of p orbitals, right? And we would have a Huckel number of electrons. And so the only one of these compounds that's aromatic is compound number 4. The next one says, which one of these compounds is non-aromatic? Well, again, in the interest of time, I'll go over this one kind of quickly. But the first one is pyridine, and pyridine is definitely an aromatic compound, and we went over that in detail as to why that is. The cyclopentadienyl cation, number 3, that is anti-aromatic. It's one of the few anti-aromatic compounds. I just covered that. Number 4 is the cyclopentadienyl anion, right? So there is a lone pair of electrons right here. If those are in a p orbital, there we go, then we would have a Huckel number of electrons, right, in unhybridized p orbitals, and that would be an aromatic compound. And we went over that in detail in class, and we explained why the pKa of cyclopentadiene is so low. Okay, so this is an aromatic compound. And this last one is also aromatic, right? This is an sp2 hybridized carbon. We have a continuously overlapping system of p orbitals, 4n plus 2. When n is equal to 0, then we have 2 pi electrons. Boom, we're good. So that's an aromatic compound. The only one of these that's non-aromatic is this one here because you have an sp3 hybridized carbon just chucked in there, okay? So it certainly doesn't have a continuously overlapping system of p orbitals. All right.